Welcome to a read along with Dr. Pell in the book Discrete Perspectives in Mathematics. This is subsection 6.4.4, High Powers in Recursion. All right, so let's suppose there's an example here of a sequence called the Fibonacci sequence, and it's defined by taking the previous two entries, adding them together, and getting the current one. 1 plus 1 is 2, 1 plus 2 is 3, and so forth. All right, so there's a way of using matrices and high powers of matrices to actually come up with a nice formula for Fibonacci sequence, the general term. First of all, how do we think about this in terms of a matrix? Well, I mean, we're taking this guy and it's the sum of like two previous things, okay? We're going to create a map that shifts forward, okay, that moves us forward in the sequence. We think, for instance, let's think of F1 and F2 as vectors. And let's create a map R2 to R2. So even if we thought of these as standard basis vectors, the shift map should be something like this. Okay, so F1 will end up at F2, and F2 will end up at F3. Okay, so we need to be able to write F3 in terms of F1 and F2 if we want everything written in terms of F1 and F2. Well, here the recurrence gives it to us right here. So we can think, okay, F1 will go to F2, which is 0, 1, and F2 will go to F1 plus F2, which is like 1, 1. So we can think of a matrix, 0, 1, 1, 1, and think. So 0, 1, 1, 1, acting on F1, F2 will give us F2, F1 plus F2, which is the same thing as F2, F3. So every time we multiply by this, two consecutive entries, it takes us one step further along. So for instance, so this times this would yield one place further along. So this guy would be right there, and then you have a new element right here, Fn. Okay, so let's come up with a formula for Fn in terms of matrix multiplication. So F1, F2 would be like this raised to the first power times F0, F1, all right? And then this guy would be then F1. Notice this is interesting here because we're doing the same. So F1 and F2, 2 and F3, F3 and F4. Okay, so this line right here is the same as this one, except we added something else. We put a 1, 0 here. What does that do? Okay, well, we know that, let's see. Well, if we just matrix multiply this and this, what do we get? We get F1. And so then we just have to multiply that to this side right here. And we should get, the top, the top entry of whatever this is, and that should be F1, right? Just like it was here, because this is the same as this over here. Okay, similarly for F2, notice for F2 we have a square, F3 we have a 3, and so forth here. And so in general, Fn will just be this computation right here, 0, 1 times this matrix to the nth, and then where we began at F0, F1. Notice this n is here if we have a 0 here, F0, F1. So if we had a nice formula for the nth power of a matrix, we would be done. We would have our formula for Fibonacci sequence. In fact, that's what this section is about. It's finding nice formulas for nth power of matrices. So let's look at that. So we're going to let A be this, and we can compute it, the determinant when we say x minus. So we put x's on the diagonal here and subtract off the matrix. So get something like this. Multiply it out, get this. That's the determinant. And we can mod out by that if we like. In fact, that's exactly what we do here. We're just, it is possible, thinking about this matrix actually is symmetric, so you could do an eigenvalue thing with it. However, in this problem, chose to do a just a modular arithmetic. We're just solving for a and b, knowing that xn is equal to something times that, where we're just modding out. Now this is interesting. Look what I did. We factored this, but when it factors in this way, where these are the different roots of that polynomial. Okay. And so we plug in these two values one at a time, and we have two different equations with A and B. So we can just solve for A and B. Um, so here to help us with the arithmetic here of that's happening here, I'm going to let R be equal to that and S be equal to that, and just think about things in terms of symbols. The equations just turn out to be that. So let's subtract. In subtracting the two equations, because the b's go away, we just get this. So A is equal to that, R to the n minus S then over R minus S. And putting this equation in the second system, okay, so solving for B, you end up, let's see, okay, and this, so the Sn is equal to S, and that's A then plus B. Okay, now here I do a little bit of computation here. Multiply both sides by R minus S, and that gets rid of that R minus S there. And then solving for R minus SB, we do that. Okay, so notice we distribute and cancel a little bit, and then divide out by R minus S this way. So B is equal to that. So we get A is, so we get A is this, and we get B is this. Okay. So the matrix A will be the same as just what we just found, A times B plus B. Okay, so we're going to stick in the matrix. Okay, yeah, okay. Matrix A to the n will be the same as this. So let's just take a look at this for a minute. Where in this calculation, oh, there's a little bit of a typo here. All right, so we'll take a look at that. So let's just suppose this is a 1 here. And your version of the book that you're looking at, hopefully by the time you see this, that typo is corrected. Okay, so we have a 1, 1 here. Why is that? Because if you add by a constant b, it's just a 1, 1. So that, and so you end up getting this. So it was correct on this line, just a typo on that line. Okay, so the calculation of Fn is simply going to be, you take, okay, so this right here is, okay, so this is our matrix right here. This is what AN is equal to. So AN is going to be equal to this actually from our modular arithmetic calculation. So we're going to throw that in here. Our calculation of Fn is, because this is F0 and that's F1, this matches what our calculation was above. And if we keep going, 1, 0 only picks the top of what comes before it. Okay, so 1, 0, pick out the top. So it'll just pick out BA actually, which is kind of nice. Just picks out BA, 1, 1. And so we actually end up just getting in the calculation A plus B, which is kind of nice. And we found out A was this, and we found out B was that. So Fn is just simply those two guys added together. We can factor out 1 over S minus R and just get this, and then using our roots, putting things back in, using these facts right here, plugging back in, we actually end up getting this nice formula for the Fibonacci sequence. Looks kind of fancy and square roots and stuff, but it's a closed form. It's a nice equation. You can compute a certain term of the Fibonacci sequence just by plugging it in and getting it out. So thanks for watching, and that concludes that little subsection.